Hello, my name is Mariangela Deligia and I am a PhD student at the University of Cagliari. In this presentation, I will talk about the structural optimization of composite steel truss concrete beams. During the presentation, I will first illustrate the composite steel truss concrete beam system and the scope of the present study. I will then introduce a MATLAB code for the optimization of this type of beams, and I will explain how the algorithm operates to find the optimal geometry. In addition, a case study is presented showing the application of the MATLAB code to a homogenized beam, and the results of this case study will be discussed. The present work deals with the structural optimization of self-supported composite steel truss concrete beams. This type of beam consists in a prefabricated steel truss embedded in a concrete core directly cast in situ. The truss is typically composed of a steel plate, which represents the bottom chord, a system of diagonal bars, and some couple rebars working as upper chord. As we can see in the picture, also the system for the support of the beam is provided in the terminal part of the beam. Composite steel truss concrete beams differ from the traditional reinforced concrete beams because in the former, the static behavior and the cross-section vary with the construction phase. In particular, two phases are to be considered. The phase 1, before the maturation of the concrete, when only the steel members are responsible for the mechanical resistance and the beam behaves as a simply supported beam. And the second phase, after the maturation of the concrete, when the concrete core and the steel truss contribute together to the mechanical response of the beam. During this phase, the static scheme is the one in the picture, with the beam fixed at both ends. The load during the phase 1 are the self-weight of the steel truss, the weight of the fresh concrete, and the weight of the slabs. During the phase 2, we have the dead load and the serviceability loads. Among the main advantages, we have that the bearing capacity is higher than the traditional reinforced concrete beams with the same cross-section. Moreover, the beam is partially prefabricated, and since the beam is self-supported during the first phase, no provisional supports are needed during the cast of the concrete. This allows to speed the construction schedule, to simplify the management of the site, to reduce the cost of labor, and consequently to lower the general costs. Here, the pictures show some real application of the system. In fact, on the left, we can see the construction site of a bridge, and on the right, we can see the construction site of a building. Composite steel truss concrete beams are frequently employed in Italy, and their behavior is widely studied in literature through experimental, analytical, and also numerical investigations. Although any study has been found concerning the shape optimization of this type of beams. Moreover, optimizing the geometry is important because it results in the minimization of the material use, in the achievement of sustainability targets, in the reduction of the self-weight, as well as many other architectural advantages. So, a preliminary study of the structural optimization of this type of beams is needed, and at this purpose, a MATLAB code is herein presented. The proposed method minimizes the weight of the beam illustrated in the picture. In this purpose, the geometric and the mechanical properties need to be defined. In red, we can see the input parameters, which are constant during the optimization process. The objective function is the total weight, which is the weight of the steel truss plus the weight of the concrete, and the design vector is composed by three design variables indicated in black in the picture. In particular, the variables are the height reduction at the midspan, the distance between the web bars, and the web bars diameters. Since the problem is a constraint optimization problem, the constraint functions have to be defined. The constraint functions require specific design criteria for phase 1 and phase 2 to be satisfied. In particular, the constraint functions concern: for the first phase, the buckling resistance under bending and compression of upper bars and web bars, and the maximum vertical displacement at the midspan. For the second phase, the compressive and bending resistance, as well as the shear resistance, and the maximum deflection at the midspan under the loads of the second phase. To set the constraint function, we will refer to Eurocode 3 for the first phase and to Eurocode 2 and 4 for the second phase. The flowchart shows how the algorithm globally works. The code uses the GS solver in MATLAB to find the minimum weight of the beam and on a series of nested functions able to perform the calculation of the beam during the first and the second constructive phases. The algorithm starts with a definition of the input data that I've just illustrated in the previous slide, as well as the definition of the objective function, the design vector, and the constraint functions. By entering the genetic algorithm, a first set of candidate solution is randomly defined. Accordingly, the nested functions gradually calculate the mechanical response of the beam during the first and the second phase. Then the constraint functions are evaluated. The objective function for that specific population is also evaluated. The algorithm ends when a stopping criterion is reached. But if the stopping criterion is not satisfied, the population evolves, improving the value of the fitness function to be minimized thanks to the selection, the crossover, and the mutation operations. The calculations are repeated cyclically for each new generation. This slide shows some details on the calculation of phase 1 when we have only the steel truss. A finite element approach is adopted, and at this purpose the CalFEM is used. CalFEM is a MATLAB toolbox for finite element applications. As reported on the right side of the slide, it consists of a series of functions, M files, each able to perform a specific operation, like the calculation of the element stiffness matrix and the global stiffness matrix, the computation of the nodal displacements, and finally the calculation of the element forces. But in order to perform these operations, the elements nodes coordinates matrices and the element degree of freedom matrix need to be properly specified. In the picture, we can see the enumeration of the degree of freedom considered to define the EDOF matrix. The solution of the second phase starts by applying the elastic line formula to the variable section beam shown in the picture below. By deriving twice and reorganizing the equation, the fourth-order differential equation is obtained, where it can be noticed that the moment of inertia varies along the longitudinal axis. The equation is solved by considering the boundary conditions specific for phase 2. As we can see, the beam in this phase is fixed at both ends, so the vertical displacement and the rotation at the extremities are considered equal to 0. Once the boundary condition is solved, the distribution of the bending moment and of the shear forces is calculated by this expression, where J function of x is the moment of inertia for variable height beams, h function of x is the variable height of the beam, defined as the height at the extremities minus the delta h, which is called empty function. Finally, we can move to the case study. The application of the optimization code to a composite steel truss concrete beam, considering both operative phases, will be treated in a future paper. Here is proposed an example of the optimization code applied to the homogeneous beam that we can see in the picture. The optimization problem consists in the search of the minimum volume subjected to some constraint functions that concern both the stresses and the vertical displacements. So the objective function is the volume, and the only optimization parameter considered in this case is delta h, the height reduction at the midspan. As already mentioned in the previous slide, the application of the elastic line formula to the beam with variable section leads to the boundary value problem. Once the boundary value problem is solved, the maximum stresses are calculated and the constraint functions are evaluated. The flowchart summarizes how the algorithm globally works. Since the code is set to calculate the homogeneous beam with variable section, the nested function in this case concerns only the solution of the boundary value problem and the calculation of the maximum stresses. The input parameters are specified in the tables. Among the geometric parameters, we have the span, which is considered equal to 20 meters, the height at the extremities, which is set to 2.7 meters, and the cross-section width equal to 0.9 meters. Also, the mechanical parameters are defined. In particular, we have the Young modulus E and the material weight gamma. In the picture, we can see that the load Q varies along the longitudinal axis of the beam. It results from the sum of two contributes, the dead load and the live loads. The dead load is function of the material density and function of the cross section, of the variable cross section. For this reason, it's updated for each value of the optimization parameter. The live load is constant along the beam, so it's defined as an input parameter and is set at 90 kilonewton per meter. For this case study, the optimal solution is obtained for a delta H equal to 2.0855 meters. The initial volume before the optimization was about 49.8 cubic meters, and the minimum volume after the optimization process was about 25.4 cubic meters. Finally, from the fitness function to number of generation graph, we can see how fast the code converged to the optimal solution. The code is set to plot the distribution of the bending moment and of the shear forces, as well as the maximum stresses at the optimal configuration. The constraint functions concerning the maximum stresses are satisfied. Also, the vertical displacements are plotted against the x-axis, and the constraint function concerning the maximum displacement at the midspan is satisfied. In conclusion, we can say that composite steel truss concrete beams represent very efficient solutions, especially in the case of large spans. In order to further optimize their efficiency, a structural optimization process is needed. Within this presentation, a preliminary study concerning the shape optimization of composite steel truss concrete beams is shown. The results of the case study confirm that the proposed method works properly, and it will be applied to a wide range of design solutions for this type of beams.